this module, the strengthening metals part 3, we're going to talk about the last of the strengthening metals techniques, and this is strain hardening. So strain hardening, we've actually already talked about before. In the previous chapter, when discussing the plastic deformation, we kind of talked about the slope of the plastic region, and we saw that if it's even, if it's flat like this, there's what we call no hardening. So, or very small hardening, because the yield strength, so basically the material yields, and then the force required to move it is constant. However, if we see this behavior, the red curve, we see that it yields and then the force continually goes up, indicating that the material is becoming harder and stronger as we plastically deform it. And so we call this strain hardening because it hardens while we strain the material. So it increases strength through deformation. And so this is, again, a material phenomenon that's observed in predominantly ductile metals that become harder and stronger as we do this, and we can find this out by the slope of the plastic region. Another name for this is also known as cold working. And we call it cold working because the temperatures aren't necessarily cold for us as humans, but they're cold relative to the melting temperature. So relatively low to the melting temperature of the material. And the working part is referring to that plastic deformation that we're doing. So cold working is another term, the predominant term we use for this type of mechanism. All right, so cold working, as you might imagine, if we are on an industrial scale, we're not going to produce a tensile dog bone and test it in our, mechanical frame, right? That's not practical. So instead, cold working is done by a number of other more practical processes. But again, keep in mind the deformation's at room temperature for most metals, or low relative to the melting temperature. And the primary function is that it's going to reduce the cross-sectional area, just like our tensile dog bone would. So the first method that we're going to talk about is known as forging. This is where you have kind of a blank metal, sort of standard size, and you put it in a die, and that die forces it into a particular shape, deforming it and therefore changing the area, the cross-sectional area. So we apply force to the die, which changes its shape, therefore plastic deformation. So that's one way. We can also do what's called drawing. So this isn't drawing with a pencil and a piece of paper. This is drawing in terms of what we refer to wires, happening to wires, which is to reduce the cross-sectional area of a wire type material by forcing it through a die. So we have a rod of a certain cross-sectional area. It is forced through a die. It's pulled with tension, and it elongates. And as we know, with elongation, the cross-sectional area becomes smaller. And so that's the process known as drawing. This is really common for how anybody would make metal wires, also plastic wires, they have to start with something larger and then draw it to a much finer and finer diameter. So we can draw wires in that way. We can also do rolling. So this is going to be done for plate metals or thin films, things like that. So aluminum foils can be done this way. And it's the process of taking a thick plate, again with a certain initial area, and putting it through two rollers, like a pasta roller or something like that, basically large cylindrical hardened steel, which can be rotated and force the plate to a smaller and smaller diameter. And so this is common for plates, sheets, and things like that. And so you can kind of think of aluminum foil in this way. And the last one that I'll mention, this isn't the only options out there, but the last one I'll talk about is extrusion. And so this is something that you're probably familiar with if you've ever played with Play-Doh. It's basically, you might not be familiar with it for a solid metal, but you take a billet or a piece of material, metal, and it's inside of a container here, and there's a ram that's forces the billet again through a die, and that extrudes it into a much smaller shape. So how pasta is made, if you've ever seen that at a factory, or again Play-Doh, all of these are extrusion. They're very common with polymers, but can be done with metals as well. So these are different ways in which we can more practically do cold work as opposed to a tensile test. And again, the main consideration here is we can measure the amount of cold work. So we call that percent CW as the difference in the areas. So this is the original area, this is the reduced area, and it's normalized by the original area, and that's multiplied by 100 to give us a percent. So that's a measure of how much cold work was done to a particular material. All right, so let's talk a little bit about what's happening during this cold work or during the strain hardening effect. So we know dislocations are what's responsible for that movement. But what happens as we're straining or cold working the material is these dislocations start to entangle with one another. So here's kind of a very high magnification electron microscope image, and the lines here represent the dislocations. And you can see that, over here they're kind of sparse and not very close together, whereas here they're getting entangled. Right? And so if they get entangled, that's just like the precipitates. It forces them to have more stress to have them to move. So the dislocation becomes harder, more difficult when they become entangled. So the act of moving forces these dislocations to be tangled. The other thing that happens during strain hardening or during cold work is not only do they become entangled, but we can actually generate new dislocations. So dislocation density increases during cold working. So you might remember something like this that I showed earlier, where very carefully grown single crystals have a pretty low amount of dislocations, so dislocation density, and then deforming them brings drastically up the amount of dislocation density. So we're generating dislocations, not only entangling them. So that's the other part. And so the yield stress increases when the density increases. All right, so let's look a little bit more at this idea with increased dislocation density. So the strength increases because we have more dislocations, and we can kind of rationalize that on a very small scale by looking at edge dislocations. So we've got an edge dislocation here, and the coloration and the terms here. So the green and the C represents compression, right? We had the extra half plane, so you see that here and here. And then the yellow region represents tension, because that extra half plane is kind of separating the planes below, so it's in tension or yellow. So if we look at two of these, if they're on the same dislocation plane, moving in the same direction, right? What we see is that there's an extra half plane here and an extra half plane here, and there's compression. So if these get close together, there's actually a repulsive force on these two dislocations, because again, there's this compressive stress, and those don't want to be close to each other. So there's actually a repulsion, which means that if we want to move these in the same direction, we have to apply more and more force. So basically, common lattice strains create a repulsive force between dislocations. And again, it increases the further they have to move. So it basically increases that stress needed to move them. And so this is just kind of an illustration of why that entanglement and why that increased dislocation density matter, because we're going to have more and more of this repulsion, which is going to increase the strength. And so our general trend here with cold work is that when cold work is increased, as you can kind of see here, we go from 0% to 4% to 24%, is the following things are going to happen. The yield strength is going to go up. So you can see here's the yield strength, here's the yield strength of the second one, and here's the yield strength of the third one. That goes up quite drastically, from about 250 to 400 to about 550. Also, the tensile strength is going to go up. So you can see those numbers going up as well. Also, on the negative side, we're going to see that the ductility, the amount of elongation, goes down. So if we look at the 0%, this goes up to almost 25, 0.25, which is 25%. And then it goes to a little under 0.2. And then it goes to about 1.12. So it decreases the the ductility with increased cold work. And so what that, just as kind of a short, just to kind of sum this up, if we think about cold work, so we cold work to get to a new shape, for example, right? If we have a big piece of metal, we want it to get to a certain product, we have to change its shape through cold working. What we're going to see is that we can, in fact, strengthen the material by doing this process. However, ductility is going to go down. And so ductility going down and down means that that material is more and more brittle, if you remember. So we can actually get to the point where if we cold work a material too much, it becomes brittle and then it can catastrophically fail. So that's a balance that we always have to consider with cold work, is that we increase the strength, which is generally thought to be good, but the ductility decreases, and so it becomes more and more brittle and less forgiving. You can think of it that way. So one of the ways that we can kind of counter this is by considering another type of work. So we have cold work, and this is typically considered deformation below about 1/3 to 1/2 of the melting temperature. So, again, relatively low temperature for that material. And so you can see here, this is a rolling mill, and you can see that it's making this thin sheet metal for whatever application, and it's doing it at room temperature. However, we can talk about hot working. So this is deformation above that temperature, that melting temperature. And here you see the same kind of rolling, but it's gone through, and you can see the metal is visibly glowing because it's so hot. And doing this process can relieve some of those issues with ductility and make it more similar to the material before. All right, so let me give you kind of a summary of deformation and strengthening of metals. So dislocations are primarily observed in metals and alloys. Those are what's responsible for strengthening. So strength is increased by making dislocation motion more difficult, but also increasing the amount of dislocations. And we can strengthen metals by our 4 mechanisms we talked about: reducing grain size, forming a solid solution by adding a component, forming precipitates in an alloy, and also by cold working. These are the methods that we talked about. There are others, but these are the predominant ones that we are talking about. And so the plastic deformation that results can have the following effects. It can change the grain shape. So if it's rolled, we talked about the kind of the shape of the grains can be elongated along that rolling direction. You can have strain hardening, right? So it can increase in strength. That can increase the dislocation density. Other effects that we didn't talk about specifically, but also need to be considered, is that the conductivity, the electrical conductivity, can actually go down noticeably in these materials. So that's something you would want to consider for something like a copper wire used for conduction. And also corrosion resistance can also decrease. And so something used, for example, in a ship that's going to be in a corrosive environment, that has to be considered as well. So all of those things are things to consider.